Okay, time is now 1:01 p.m. in Stockholm. My name is Martin Törngren, and I would like to wish you very welcome to this session. I see we have now 39 participants online, and maybe we can give people 1 more minute. The number is still increasing. But in the interest of time, I think I will slowly start. I would like to wish you welcome. And I think that the two sessions I will provide here will be perhaps slightly different compared to what I've seen from the other presentations. This will be a little bit more of a helicopter perspective. And this I hope you will find relevant. And the purpose of these two sessions and the overview you can see here, and there's also a meaning with this thread here. So I will be talking about cyber-physical systems, and to make this concrete, I will start by automated vehicles, and then we will generalize from there, relate to other concepts such as Internet of Things and Industry 4.0, and then reflect on what the implications of CPS are, in particular in terms of a socio-technical shift. And to manage cyber-physical systems and to be able to leverage all the capabilities that we that we will get with them, we need to manage their complexity. And this will be the focal topic of the session tomorrow. So looking into different facets of complexity, how we as humans can deal with these complexity facets, looking at how we do it today and what we may need to deal with the complexity of tomorrow. This is the outline. I will aim to have breaks, leg stretch, from 2 p.m. 10 minutes. And I'll try to respect that firmly. And then all along the way, you can see here we have Q&A sessions, and you're most welcome to post questions. We will be taking breaks for these Q&A sessions. And along the way, there will also be a number of polls. So let's get started. So to begin with, I wanted to say just a few words about myself, because that relates very much to the topics I will be talking about. I have a background in mechatronics and embedded control systems, and these are very interesting topics in their own right, and they emphasize multidisciplinarity, and I've always been interested in broader scope and broader set of topics. Last years I've been working a lot with autonomous cyber-physical systems, and you can see the topics here. MBSE stands for Model-Based Systems Engineering. And then I had the opportunity to do a first sabbatical at UC Berkeley, and that really opened my eye towards cyber-physical systems. And when I came back to Europe, I had the opportunity to be part of a number of European efforts looking at what are key challenges and needed research in the direction of cyber-physical systems. And I will be sharing some of these insights today. And by the way, of course, I will share slides and references and links and so on. And then past years, I've also had the opportunity to not only looking at cyber-physical systems, but also looking more in depth at sustainability. And it's kind of a twofold paradigm shift that we are facing on our planet. On the one hand, we have the technology shift. We need to deal with that. we need to deal with, let's say, a new industrial revolution. At the same time, we have the climate warming and the sustainability challenges. And then I have two centers in Stockholm that touch upon these topics, and I will come back to them briefly during my talk. And finally, I just wanted to mention here that if you're interested in some of the areas like automated driving, edge computing, and so on, we have quite a lot of opportunities for internships and master science thesis and so on. And if you're interested, you're most welcome to contact me. So we will be talking about cyber physical systems, and then it would be quite relevant, I think, to check what your view is of cyber physical systems. And so I have a first poll here, and the poll is about cyber physical systems. And I would like you to answer, you can only pick one answer, and just pick what you find most relevant. Don't be anxious about, there's no right or wrongs right now. I just want to get an idea what you have in mind. And then during the remainder of the talk today, I will be elaborating a lot about cyber physical systems. So I see answers are coming in. Thank you. Please go ahead and answer. Don't be afraid of answering something. Just take what you find most natural. So right now we have some 30 answers. We have 46 on the Zoom. We'll give it just a little more. Okay, let's go to 75%. We need a few more. We are now at 73%. Okay, so maybe you don't want to poll the remainder. That's fine. Let's have a look at the results then. And it's a spread. And it's nice to see that most of you actually picked the original definition of cyber physical systems. So this is clearly one good answer. As you will see in my talk, I'm really using CPS, and many of the originators of the term are using CPS as an umbrella term. There were not many answers here, but let's see if I can convince you about that. As we will see, there's a dual interpretation of the word cyber, and we will look at that. One interpretation is as feedback systems. And to me, embedded systems would clearly be a subset of CPS. Okay, so thank you very much. Then let's move on cyber physical systems. So the original definition from the US 2006 is indeed CPS as an integration of computation, networking, and physical processes. And as I'm sure you're aware, this is not new. For example, we had distributed control systems were introduced in control of manufacturing plants in the 1970s. But we are seeing an increasing scale and new capabilities. And one of the confusions here is that CPS actually has a dual meaning. So colloquially, when we speak about cyber, we will think about computers, cyberspace, cybersecurity, or other things like that. Originally, cyber was introduced by Norbert Wiener and indeed referred to feedback systems. So this, of course, may give a little bit of explanation of the confusion here, but in my take, most CPS, as you will see, they really incorporate computers, physical systems, and they involve feedback loops. So I think in many cases this is not so much of a problem. Humans are an additionally important element. And just in case now there are people here that are not absolutely sure what a feedback system is, feedback systems are essentially meaning that we have some form of control system, we are measuring what is happening, and we are adapting our control actions. This is an example of what might be a typical mechatronical control system using not only feed forward, but also feedback by measuring and adjusting to achieve the desired effect on the controlled system. Now, I wanted to have a little exercise here. I see some people newly joined. We are into CPS. So if you're comfortable now, I would like to invite you to join me into an exercise, and I will join that myself. If you're not well today, you might sit down. But so please stand up and feel relaxed, and then you raise one of your legs to some relevant level. So you stand on one leg. Now you have to work a little bit more to keep your balance. And now be careful, but close your eyes and feel what happens to your balance. I practice this a lot. I practice balance a lot. So, but now if you followed my advice here, or if you want to do it afterwards, you will feel a sensation. And the sensation is essentially that you lost one of your feedback loops. We have actually 3 feedback loops in our body. We have an inertial system for balancing. We have sensors in our muscles. And in addition, we have the visual system. And all these are used to help us to keep stability, as an example of a feedback system. And here we shut off one of those feedback systems, and that reduced the quality of the feedback control loop. Okay, so cyber-physical systems as integrations of computation, communication, and physical processes are clearly here to stay. They have been around for a while, but they will, as we see, they will have unprecedented capabilities. We are pretty far ahead in introducing automated vehicles, automated trains, automated anything in the future, automated flying aircraft, automated delivery of packages and what have you. This brings unprecedented capabilities, but also unprecedented capabilities, and we need new methodologies to deal with these systems and to direct these systems in the right ways. Clearly, we want to use these capabilities in a useful way so that they are human-centered. One important aspect of that is that we have to deal with sustainability. We are overusing resources on our planet. There is something called the overshoot day, and the resources we are using we are actually depleting the earth of resources. And we are into an economy where we are taking raw materials, building things, and then using them and then throwing them away, creating large amounts of garbage. We are polluting the air and the water. If you look at the World Health Organization statistics, I was actually shocked to see how large part of our population on the planet that have severely poor air quality below the recommendations. And then we have this very subtle but already present and emerging threat of climate warming, which will likely have devastating effects on our planet. So basically, we really want to leverage the CPS, and to do that we need to manage complexity, and then we can, for example, and importantly, leverage them to deal with our challenges like sustainability. And this is really some of the main thrusts of this talk. But in order to do that, there's another challenge we have to deal with, and that is basically dealing with ourselves. So technology is evolving at an unprecedented speed, but we are not evolving at an unprecedented speed. Our brains were forged on the savannah more than 10,000 years ago. Our behaviors are still representative of that environment. And that creates challenges in dealing with these threats and the complexity. And that's something we will be talking about as well. And essentially, the structure relating to that overview here is that we will today talk about automated vehicles as an example of CPS, and then about the implications of CPS and the capabilities and how we can address sustainability. And then tomorrow I will be following up by talking about how we, what is complexity? What are the facets of complexity? What are our limitations in dealing with them, and how might we deal with them? So that is the sort of menu, and I hope you will find that interesting. And let's now embark on to automated vehicles. And in doing that, first a bit of a pause. This is, I'm sure, your home territory. You're all familiar with Moore's law and so on, but I always find it kind of fascinating to look at the computer that brought people to the moon for the first time in 1966, and what we have today. And as you know or can see, we have factors of roughly a factor of 10,000 when it comes to speed, memory, capabilities, and of course the cost efficiency advancements have been enormous. And that has brought us computer systems being integrated with the physical world in all kinds of places. Here's a typical mechatronics example from Scania, and truck manufacturer. And although diesel engines are becoming more and more obsolete, this is very representative of a mechatronics module, a diesel engine, or if you like, an electrical engine or a gearbox or what have you. And we have the computer system firmly mounted directly onto the mechanical system, a cyber physical system, or rather a cyber physical component through which we can create cyber physical systems. And it's interesting to note the interfaces. So we have the mechanical interfaces, we have energy interfaces, and we have information interfaces, in this case through the so-called controller area network. And if we look at the evolution then in mechatronics in particular, well, mechanical systems were around. We built cars before the 1970s, and they did not have computers. And then in the 70s, one started to integrate computers to improve performance, for example, of the engine, or to improve the performance of the brakes, the automatic, the ABS systems to improve the braking performance. So we were essentially forming these mechatronic modules. They were still connected mechanically. And then after a while, we added networks. And from the perspective of physical systems, you see similar trends in different domains. So in factory automation, these networks were added in the 70s, in aerospace in the 80s. In the automotive, controller area networks emerged in the 1990s. And now today, of course, we have wireless external connections. And this then summarizes one view of cyber physical systems, where we have physical aspects on one side, like in mechatronics, the laws of physics, Newtonian mechanics, and the information side, the cyber side, with logical connections. Okay, so where has this led us? Well, it means that we have gradually introduced these systems, and we have introduced automation. In the beginning, we had automation using mechanical and electronical and pneumatical systems to do simple logic. And then we introduced computers, and typically automation was about relieving humans of doing dirty work, dull work, or dangerous work. For example, here you see a view of a robot doing welding, and computers are very good at doing these repetitive tasks. And we put the robots in a cage. And essentially today we are removing these cages in factories and on the streets. We are putting robots into society. And then when we talk about that, we talk about levels of automation. And as I indicated, this is not new. Sheridan and Parasuraman studied that a long time ago. And there are different dimensions of automation. I just wanted to show you some of them before getting to automated vehicles. So you can talk about the horizontal axis here, what you automate on one hand. If you think about, for example, the control system we had before, the feedback system, you might think about automating only information acquisition, or perhaps just decision support. You can automate different parts and to different levels, meaning more or less able to act without humans. So these are two dimensions, and then we have additional dimensions which could be related to typically what is the environmental scope, what is the complexity of the environment and the capabilities or the tasks, what is the complexity here? And this is essentially what we are seeing with automated driving. So in automated driving community, they took these old taxonomies. Yeah, it could also be multi-agent. And they created a taxonomy for automated driving. And I think many of you have seen these levels of automated driving. There is a very simple interpretation here, a bit simplified, but talking about feet off. That might be like adaptive cruise control. The longitudinal control is automated. You still have to steer. Hands off. Now the car also does steering for you. For example, like automated driving in the lane on the highway, acceleration, braking, and steering. But if you want to change lane, you still have to do that. So feet off, hands off, eyes off. That's what we call level 3. Now the car can go from point A to B, but you as a driver, you as a person is still responsible. Mind off means that now you're not responsible anymore within a restricted environment. So going from point A and to B on the highway, you don't need to be present. You could look at the movie. You could perhaps even sleep. But this is not as trivial because these regions where automation is implemented could be smaller or larger. So likely you would have to take off or the car would have to stop, but it would have to do that automatically. And level 5 basically means automation present everywhere. Okay, so these are the levels, and you can see here that there is kind of a complexity involved. Yes, and I will be making no distinction here talking about automation or autonomy, and I will also be using AV and AD synonymously. So now it's your turn, and let me start the second poll here. And I hope you want to join this poll. And again, don't be afraid, just throw out what you think might be a right answer. We will be looking at this in the follow-up. And of course, this might be difficult if you're not into the area, but just pick one option that you think is incorrect. So one of these options is, in my view, incorrect. Okay, please go ahead. Don't be afraid, just fire off. We will look at those questions. So the SAE J3016s are the automation levels that I introduced before, level 0 to 5. Level 3 is the one where you as a person is still responsible, but where the car can actually go from point A to point B. Level 4 is where the car can do fully automated driving in the limited area. Let's see, we have 51% have answered so far. Let's give it a little more. Still increasing. Can we get to 75%? Okay, a few more votes, then we are at 60%. Come on. Just a few more. Okay, looks like we stopped there. So I'm ending the polling now and I'm sharing the results. And hopefully you should be able to see the results. And so which one is incorrect? So there are indeed very big gaps. You might argue that the gaps are not as big between each level, but in particular level 2 to level 3 is a tremendous gap. Level 4 to level 5 is an enormous gap. Level 3 to 4 also has a gap that we will be looking at. Let me see here. Yeah. So most of you were actually picking answers 3 and 4. And we will have a look at that. But actually, level 4 has only very recently been on the roads. And that is the new Waymo service, where they not only until last year, late last year, removed the supervising person in front of the steering wheel. So, yeah, sorry, that was alternative 4. So number 4 is correct. And number 3 is also correct, as we will see in a while. And just to summarize here, the not correct answer is alternative 2. Okay, so let's elaborate and move on there. So, what is automated driving about? Well, on the face of it, it doesn't appear too difficult. An automated vehicle needs to know where it is. It needs to know what the surroundings look like, static objects, dynamic objects, and what the intents are of the dynamic objects. To do that, it needs to do observation. It needs to use pre-stored information like maps. And if we know that, well, then basically we can plan and we can generate trajectories, short-term, longer-term. We can implement that in terms of control and feedback loop systems using the vehicle platforms. So how difficult can that be? Yes, let's look at one example of Waymo. And as you know, Waymo is the formerly automated driving of Google, which is now under the umbrella of Alphabet. And as you can see here, as you may know, and it's interesting to Google on the history, there has been a lot of research on automated vehicles. For example, in California, in the PATH project, they had automated vehicles running in convoying in the 1990s already. There have been quite a few demonstrators around. DARPA Grand Challenge was really pushing it, but as you can see here, this was one overview. Google, Waymo have been working on this and are in many ways leading the work on automated vehicles. And there was a statement here, fully self-driving was not available then. We still had level 3 automation capable cars, but still a human supervising and taking over when needed. And it was only until last year that fully driverless cars, the test driver was removed in some of the vehicles run by Waymo. So in most of the driverless vehicles that are being tested, you still have a person present. Of course, you have automation in other areas, and we will come back to that and how that might differ. But the takeaway here is that it takes time. We have been working on automated vehicles for quite a long time. So how difficult can it be? And then a follow-up question here that we will have a look at is why has it taken time? What are the biggest problems? So let's look at, oops, sorry, I was launching the wrong one. I want to launch poll 3 here. And poll 3 is about why has it been so difficult in launching automated vehicles on our streets? Again, only one answer, and don't be afraid here of just reaching out and picking what you find most relevant. As you can see here, these answers really indicate different type of aspects. Okay. I see here to the coordinator here, I see that there is one person online that doesn't see the polls. Okay, using Zoom in Linux. Okay, sorry about that, but I will share the slides and you will be able to have a look at them in detail afterwards. Okay, we are reaching 60% here. We have 65 people online and we have 60% voting. Okay, let's have a look at the answers. And hopefully now you should be able to see them. Thanks a lot. And you can see here the very strong domination for the first one, lack of regulations. And yeah, my simple take on this is really that this is a combination. Each of these are really barriers to introducing automated vehicles on the streets. And these barriers might be higher or lower depending on where you are, depending on, for example, the regulations in certain countries. And depending on how strict the safety assurance is. So thank you very much. Let's follow up on this. I hope everything should be clear while going through this. So how difficult can it be to go for automated driving? So first of all, of course, we need a lot of sensors. The automated car, it needs to understand where it is, where other objects, static, dynamic, are. And so as we had in the previous slide, the question, getting good enough perception, knowing how many sensors do we need, how much of diversity, what are the failure modes, reliability, what about the cost of these systems, what about the maintenance of these systems. There are lots of open issues here. And another key aspect here is really that when we are putting robots on the streets, automated vehicles, of course, there are different environments. We could constrain them. Ideally, we would build entirely new roads which are prepared for automated vehicles. But this is not what has happened primarily. Instead, we are putting vehicles in very complex environments. And as Herbert Simon once said, I have a reference, I will follow up on him later on. He said that the environment and the mission in the environment is really the mold, is forging the systems we are building. So if we have complexity here, well, certainly we need complexity in the systems we are deploying to manage this complexity. We need sensors, we need a lot of processing, we need sensor fusion, we need to reason about what is going on, we need to do the planning and so on. And to do that, obviously, we need heterogeneous supercomputers to deal with different algorithms here. And moreover, this is reflected in the expertise and the organizations. So we have unprecedented capabilities and complexity here. One important aspect of that, when replacing a human driver with our capabilities, with an autonomous driving intelligence, is that we somehow want to mimic or emulate what humans can do. We need the motion control system. We have our cerebellum, and actually, the ones who joined me in the stand-up closing your eyes exercise, we were then exercising our motion control system, the motion control coordinator in our body, in our brain, the cerebellum, the little brain. And we have a capable system there, but we can program, we can develop these systems. Then humans have a fast way of reacting to learn situations, to think fast, according to Kahneman. We can basically program these systems. What we have a difficulty in doing today is really to think slow. We can deal with situations as humans to a large extent that we haven't seen before. With experience, we can deal with unknown situations, and that's something we really don't know how to program in a systematic way. So that is a related challenge. Now, given that this takes so much time and that there are enormous investments into automated driving, it's very interesting to reflect on what is pushing automated driving. And there was an investigation made, published in the MIT Tech Review. And essentially the result, which you could, of course, argue a lot with, it's difficult to monetize these things and monetize the lives of people for sure. But in any case, the result here from this survey was that it's pretty clear. We are transporting enormous amounts of people and goods. It's a huge market. And a big portion of the cost here are the drivers, the chauffeurs, the truck drivers. They might be scarce. It's a fact. So we have a huge market here that's really driving the whole thing. And I think it's important to be aware of this very strong economic drivers. The automotive industry will likely tell you, why are we doing this? They're probably going to have health or safety at the top here. But in actuality, it's a big market. And so it's actually a gold rush. Confucius said we should call things by their proper name. And I think that it's important in this situation because we are seeing these enormous investments in parallel, very little collaboration, money flowing from the US to China, from China to US, for example. And the key question is, when will the gold emerge and who will get hold of it? And we will come back to the gold rush when generalizing. Okay, so how are companies dealing with trying to get there to high levels of automated driving? There are different business cases. So you will see that some of the, especially the new players, they have decided to not go for level 3 because of automation problems, knowing who is in charge. So they have therefore decided to go for level 4. And that's the example of Waymo. The traditional car manufacturers are instead going the other way around. So they are slowly increasing the level of automation. And in the context of automated driving, we talk about the ODD, the operational design domain. That's really the scope. Can my automated car deal with automated parking, limited situations, automated highway, automated something bigger scope? And as you can see here, there are different approaches here. So for example, the Waymo cars in Arizona have a rather limited operational design domain, very well mapped environments, well-controlled environments. On the other hand, if you go for automated highway driving, you might be able to do automated highways in many parts of the world. So somewhat bigger operational design domains, different approaches. So a few more observations here before we wrap up on automated driving. Automated vehicles will clearly have societal, socio-technical, societal impact. For example, once we have them there, will we need parking lots in cities? We could perhaps even redesign entire cities. The behaviors of people will likely change. And as we see, we have this enormous transportation market. We are creating new vehicles with new sensing, new compute capabilities, and getting hold of much more data. It's a whole new business ecosystem, new collaborations, new partnerships that are being created. And it's an extremely interesting research area that actually touches upon some very deep topics like ethics, who is responsible of the behavior of an automated vehicle, and beyond responsibility, what is an appropriate notion of risk for an automated vehicle? How should they behave? We are building systems where we are building into the systems, we are building notions of risk, online risk metrics, online assumptions. Being aware of them and discussing them is very important. And with automated driving, there's a very interesting debate going on relating to this. And it has to do, when can we release an automated car for driving on the road? Can we have a driver test for an automated car? What can happen? How many tests do we need to do? When are we done? It's an extremely interesting research area. What is also interesting and a bit surprising in one hand, as I said before, the street environments are not prepared for automated vehicles, and yet we are putting cars there. And really the most difficult situation we can think of, if we had collaborating vehicles, collaborating with infrastructure, that could facilitate a lot. But that assumes we have the infrastructure in place. It assumes we can rely on each other. There's also little, or at least too little, emphasis on both safety and security and their interactions in the context of these interconnected cyber-physical systems. And this is really a topic that is going beyond automated vehicles, as are the other ones, as you will see when we continue after the leg stretch. So wrapping up automated vehicles, first of all, as I briefly touched upon, automated vehicles means a lot. In the subway of Paris, there are already some lines which have automated subway trains. And what characterizes these subway trains? Well, it characterizes a very limited operational design domain. It's a controlled environment, an enclosed environment. So in controlled environments, we are seeing, and we will be seeing, much more faster introduction of automated vehicles, like in factories, because we can control the environments, or in perhaps in mining, or in road construction, building construction. So we have many domains and many business cases. That's important to keep in mind. And then automated vehicles, as we had in one of the polls, it's really touching upon all kinds of things. The legislation is not there. The legislation still talks about, or it's evolving, but it still talks about people having the responsibility. The transportation systems, as we said, they are assuming people. The traffic signs are designed for people. Life cycle operation will change. We talked about new ecosystems. We talked about risks and ethics. It's really changing all things we can think about. So a very rich area, but as I will come back to, also very representative of other CPS domains. And in particular, perhaps for researchers here and engineers, we don't only have all these stakeholders and aspects that are affected, but we also have all these disciplines. And here we are seeing an unprecedented need for integration of these disciplines. For example, how do we reconcile safety, security, and AI? How do we reconcile that with, how do we deal with robotics, complex systems, and so on? Okay, so this concludes the first module, and I would now like to take just a little break. And I see here that unfortunately polls are not available on all browsers, but hopefully you still have some questions, or if you have questions, you're most welcome to launch them right now. Eneko, have you received any other questions from your side? Do we have any questions? I'm looking into the Q&A window and I can only see questions about the limitations of Zoom in certain browsers or operating systems. Okay, I don't see any questions.
Martin, sorry.
Yeah, please, go ahead.
You should have also a Q&A tab in your Zoom menu, not the chat, but the Q&A.
Okay. Sorry about that. I was looking at chat. Q&A. Right. You're so right. Thank you. Sorry about that. Yes, thank you. I do see 3 Q&A questions here. Okay. In which direction do you see further development for automated vehicles? Right. It's related to what I talked about. Will we try to get the vehicles on the street, or will we have to change the streets to enable automated vehicles? Excellent questions. As I said, it would be much easier if we actually did change the streets. And there are experiments going on. Actually, by coincidence, I remember an interesting panel debate with the car companies many years ago. And there was a similar question then. There was a question to automotive companies. What would be your dream asset? What would you like to have to push automated vehicles? And the reply was, I want a city. So a city to experiment with. And we are seeing such cities and streets being built. China has been mentioning new streets and cities being built explicitly for automated vehicles. There are test environments being built. So I think this is a very important direction, but the mainstream developments are still putting the vehicles on the street. And it's, I guess, a kind of a balance here. If you can manage that challenge, then you will really be able to leverage that. And so it's still an open question. But the general direction is really that we need more efforts also on changing the infrastructure. So one more question. Will we talk about software system architecture? I'd love to go into that. I will be touching upon architecture, but only briefly. There will be a bit more also in the next section, so please feel free to come back to me with more questions and I can perhaps give some more pointers. Two more questions and then we will move on in the interest of time. Thank you, Jasmine, for those two questions. And then Alvaro writes, do you think that hardware accelerators have a place in this business? And I think the answer is pretty clearly yes. We are seeing that in the automated driving, but also in all kinds of CPS, that the systems are becoming more heterogeneous because we are fitting more functionalities, more algorithms that have different characteristics. So data intensive, compute intensive, and so on, different types of computations. So I think this is really what is going on. And there are competing architectures. It's very much evolving with GPUs, FPGAs, multi-core distributed systems. So the answer is yes. And maybe we can come back to that topic. And Kim writes, Copenhagen also has automated subway trains. Yes. Yes, so as I mentioned, we already have quite a lot of automated things. So automated in the limited sense, typically meaning limited operation design domains. And actually, if you think about an automated, if you think about a modern car, even if you think about a car 10 years ago, it has a lot of functionalities like vehicle stability control, cruise control, and so on. They are all partly automated functionalities, but not yet at the levels of automated driving. So thank you very much for these questions. And further questions are welcome. And then we have a few more minutes for the break. And I wanted to get started on the moving on from CPS to the generalization. So as I alluded to, some of the trends we have seen here in the automotive industry, we are seeing electrification in terms of electrical energy provided, for example, through the streets or through electrical power lines, electrical power trains and batteries. That's one general trend. It's not happening only in the automotive sector. We are seeing connectivity in the automotive, but in all sectors where we talk about connected things, Internet of Things. We are seeing higher levels of automation and smartness illustrated by an early Google automated driving car. And we are seeing the use of connectivity and automation and cloud to create new services. And this is happening essentially in all domains. But because of the huge investments, I think probably the strongest driving sector above all now is automated driving. But it's happening, for example, also in manufacturing. And what does this mean? Well, it means that we have all these concepts and others, and they are all reflecting what is going on. They are reflecting these trends, but they have different perspectives to these trends. And of course, I will be highlighting CPS, but also having a look at how it relates to the other concepts. So if you look at CPS definitions, as you saw, the original CPS definition talked about combining, integrating computation, communication, and physical things, creating synergies, which, by the way, is the old definition of mechatronics, synergies between mechanics and electronics. So this is one interpretation. In the the German Science Foundation, in their interpretation of CPS, they recognize the above one, but they're really emphasizing the cyber dimension as the new aspect. And there's a very interesting story connected to this that it's worthwhile sharing. And essentially, the story goes that the Germans early on picked up this new thing, cyber physical systems. That's really important. We need to do something. And then in the dialogue with politicians and industry, they came up with a new term, Industry 4.0. So CPS really in Germany became a domain-specific interpretation. So CPS in the manufacturing domain is what the Germans call Industry 4.0, but with a specific emphasis. And then, as you know, IoT really emphasizes connecting stuff out there, but more in a kind of a bottom-up way. CPS is more systems-oriented. We are actually not just connecting, we are creating systems. And here maybe the interpretation is a bit more of creating potential services. Many of these definitions that we find are very general. In a sense, these definitions that we have for CPS, they could really mean any system tomorrow. Which system tomorrow will not have an integrated cyber and physical parts? A lot of systems will have that. So it doesn't really say that much. And that in the European projects I talked about, that led us to instead going into, let's say, a very high level or a very stern definition, instead to go into a characterization. And I wanted to touch upon that briefly before going into the break. So when we talk about IoT or CPS, for that matter, I think, and what we recommended here, it really means that we need to clarify what we mean. So, for example, Industry 4.0, the German interpretation was really more on the cyber side. If you clarify that, well, people will understand what you mean. But some people might mean innovations, let's say 3D printing, more on the physical side, the material side. You can talk about different operational design domains. What is the domain you're talking about? Are you talking about stationary or mobile systems? What is the level of automation, decentralization, role of humans? What about life cycle connectivity? And what about talking about a system like a car versus a transportation system, a system of system where we have multiple organizations, things can change without the car manufacturer even controlling it. So I think this is helpful to keep in mind when we use these terms to actually clarify that there are types of cyber physical systems, there are a type of Internet of Things. And I think that I would really like to conclude here. We will be starting off in 10 minutes from now, roughly, 10 minutes past 2. And I would like to start with this poll, and we will be continuing on the generalization and spending the last part on looking into cyber physical systems as part of a socio-technical shift. And with this first part, I would like to thank you very much for your attention. We will keep this stream on, and I will be back in 10 minutes from now. Thank you, and see you in 10 minutes. Ciao. Okay, time is now 2:10. Welcome back. And let's get started. So, we are talking about cyber-physical systems, and we were talking about the generalization. Maybe we could just take a step back. Yes, the last thing we talked about was the fact that we have different types of cyber-physical systems, and it's important to characterize them to clarify what we mean. There are different types of systems. And in moving on, there is a quiz, a poll, and I will start the fourth poll right now, hoping that you are ready to go ahead. There is one correct answer, or correct at least. That's the answer I got from Atlas Copco Industrial Technique in Stockholm. So they are developing these professional assembly tools. It's kind of a screwdriver, but they are quite professional. They are very accurate. They are storing what has been. They can trace back, for example, from an aircraft, each individual nut that's mounted in some place can be traced back all the way to manufacturing to know how it was manufactured, when it was manufactured. Because many of these joints are, of course, critical. You don't want the wing to fall off an aircraft, for example. And moreover, if these tools fail, the assembly line, the production may actually stop. So they have to have high availability also. Okay, we are approaching 50% responses here. Maybe just a few more. Okay. Thank you. We have close to 50, maybe just a few more could vote, so we get. Okay. That was the Q&A. Yeah, thanks for the Q&A. I'll come back to that. Okay, so 50%, great. Thank you very much. So let's share the results. And you are very knowledgeable and you got it right. The answer I got from Atlas Copco is indeed 500,000 lines of code, which is kind of surprising. You would think, how difficult can it be? And I did, a friend of mine helped out with an experiment. We were actually estimating, now if we print 500,000 lines of code with some assumptions on lines of code per page, it actually meant that we would get 8,000 pages, 1.5 meter up in the air pile. And that really says something about understanding or limitations of understanding these 500,000 lines of code. And why do we have that? Well, program is an extremely powerful tool, and we will get into that in particular next session. But we have powerful abstractions, we have libraries, we can build new services on top of existing ones. Also, if we look at functionality, just like if you think about the cell phone, core functionality, well, that's a call, right? Making calls, but we are using this for so many other things. And here we don't just have the controls, we have interactions with humans, we have communication protocol, we have diagnostics. These things are availability critical, as I said, so they want to make sure they don't break down before we know it. So they have diagnostics, predictive maintenance. There's a lot of software at the different levels, like protocols, operating systems, and so on. There are safety measures. You don't want to harm people. You have different modes of operation, testing mode, calibration, updates, and so on and so forth, ending up with 500,000 lines of code. And why am I bringing this up? Well, we talked about CPS, and we said that we had these common trends like automation, services, connectivity, and so on. And that's true in many domains. And under the hood, we then have software as one essential enabling technology. Another such enabling technology is that of communication, the connectivity. And as you know, we have many types of communication. We have many types of connectivity. And what's very interesting now is that we are seeing that these things are coming together. So if we look at a modern truck, for example, when you buy it, it will already from the beginning have wireless telecommunication connections, 3G, 4G, to the manufacturer cloud, but not only to the manufacturer cloud, also to the operator cloud. There's perhaps an operating running fleets of vehicles to do some particular transportation. There will be connections to workshops and so on. So we are seeing different strands of communication, telecommunication, short-range wireless, internet, and computation. And all these things are coming together. This is just one other example of smart meters that in many countries have been connected since many years. And what does this mean? It really means that one facet of this is that the world is becoming a distributed connected system. A la division of Internet of Things, but also using different types of communication. And of course, since we know that many of these systems will be cyber-physical in nature, the world is becoming a distributed cyber-physical system of systems. And what is happening then in the connectivity domain, this is a somewhat involved figure, but I think you are pretty knowledgeable in this field. 20 years ago, people started to talk about the cloud. Today, clouds are everywhere. We are connected to them through our cell phones. We use cloud services every day. And companies have their own clouds, like we had, for example, the example of a truck being connected to a manufacturer-specific cloud. Then we have the smarter devices that are growing in scale and capability. We have gateways, but then we have kind of a new domain, just like we talked about cloud 20 years ago, we're today talking about edge computing, which is projected to have the same impact as cloud has had. And really what it means is that there are different strands here. So the telecom will talk about mobile edge computing using base stations to add local computational capabilities, or fog computing using things like routers, gateways for local computational capabilities, or thinking of distributed decentralized clouds, adding a local computational server. What this means is that in common is that we are adding computational capabilities locally to augment what we might have or cannot add locally. For example, a base station might be able to serve traffic or societal services in the neighborhood. And this is all driven then by limitations when it comes to real-time latency to the cloud. And it's driven by the limited resources here, privacy issues, and the need to deal with the large amounts of data. So this is an exciting future and developments. One interesting reflection here, we talked about heterogeneity, that we have embedded systems are very well known. If you just look at, for example, the operating systems in embedded systems, well, we know that we found a plethora of different real-time operating systems. It's very heterogeneous. And while the further we go to the cloud, the more homogeneous things becomes. And it's interesting to see where the edge computing will end up. But this is another domain where lots of things are happening and infrastructure is being added. And then given computation, communication, sensors, and integration and the physical capabilities, we are ending up with cyber-physical systems that will have entirely new capabilities. These include cyber capabilities, so dealing with data, of course, being able to use data to do awareness and prediction, all the way into a scary future of reading minds, reading intents. And then, of course, the cyber part can plan and make decisions. But beyond that, CPS of today will also be able to create, generate, synthesize not only software systems, cyber systems, but also physical systems. Think about additive manufacturing, for example. So there's a synthesis capability across the CPS aspects. Moreover, CPS will not only be dealing with the cyber domain, it can also control and generate energy, might be self-sufficient when it comes to energy, and it can, of course, interact with humans and with other systems using various modes of augmented or virtual reality. And all these capabilities can be applied now, short-term horizon or longer-term horizons, in the local perspective or the larger scope in terms of a system. And this is then, I think, this is reinforced by innovations in many domains, from sensors to compute to new materials. And then we have the interesting facet of having humans and CPS to collaborate using the strengths of humans and CPS. So I think this is just my current take on this. I think this is an evolving, it's just mirroring the very interesting evolution of these capabilities that we have. And then there are lots of follow-up questions, and one of them would be, how can we make use of these capabilities? How can we leverage them? And although kind of perhaps implicit, if you look at some of the roadmaps I mentioned, if you look at the visions projected, we talk about deploying CPS in all areas. We can talk about CPS to control water. This is partly already in place, but increasingly so in controlling, managing traffic, controlling, managing energy. So we will find this interconnected CPS increasingly in all domains, and as I said before, a world filled with CPS OS. Right, and then in particular, as I mentioned in the beginning, we really want to leverage CPS to deal with sustainability. Sustainability, as you may know, is kind of a complex thing in itself. When we talk about sustainability, we talk about environmental sustainability. We talk about other aspects of sustainability as well. We can talk about sustainability at the societal level and for economy. So how could we leverage CPS and CPS OS? I think one very important aspect here, because we have the climate warming crisis, is to actually see how we can use holistic CPS and CPS design to remove or reduce carbon dioxide emissions, or even to capture and deal with the carbon dioxide out there. What is really challenging is that things are so connected. If we think about smart energy systems, solar cells, on the one hand, they are produced in some environment that might have environmental effects, CO2 effects. They are transported, then they're actually used, then they are repaired, decommissioned. It really necessitates a holistic view. If we do these things in the wrong way, for example, if we do use electrical cars, well, that seems to be useful, but if the electricity is produced by burning coal, we are actually we are just shifting the problem to another end, and we are likely to produce more carbon dioxide. So we need to look holistically at this. Of course, with the CPS, one prominent aspect is that we can measure, we can control, in particular, the use and management of energy. There is another concept which is very important here, and I want to expand a little bit on circular economy, in case you haven't come across that. And I did touch upon that before when I said that we now have a linear economy. We want to go beyond the linear, take, make, dispose, create a lot of garbage. We want to use a circular economy, and what the people working with that, they would say that it is restorative and regenerative. And you can see here the three principles, and there are different perspectives of this. And perhaps one of the key ones here is really that one way to see it is that you actually don't even think about waste anymore. You don't want to create waste. Instead, you look at, for example, in a production, you're producing things and you have leftovers, but leftovers, instead you look at them as assets. How could you use them? How could you sell them? And how could you make sure that they become part of a circular economy, not to waste resources, including creating unwanted side effects like carbon dioxide. And then there are some keywords here in this cycle. There are interesting and important implications. So one implication is don't throw away, instead increase the lifespan of products and services. And that means to maintain, prolong, reuse parts, redistribute, for example, remanufacture. And one implication of that goes along with one of the general trends I talked about before. Instead of selling products, selling a transportation service or an assembly service, the professional tool, instead selling that as a service. And that would give incentives for the companies and the supply chain to actually not create waste, not to make people scrap, buy new, but instead to have a service promoting this circular economy. So let's look at what does that mean for the CPS. How can a CPS promote a circular economy? So some of these things come very natural with the capabilities that I mentioned for a CPS. So if we put a small cyber part, it could be just an RFID tag identification. It could be helping to identify and trace. It could be more like measuring more properties to help monitoring, prediction. If we can know more about the state of a component or a part, then that will help us in taking decisions about reusing, recycling, and of course, with the software-based product, it becomes easier to upgrade or even downgrading products. This is already happening, for example, with trucks that today, or cars for that matter, that come, but in particular for trucks that for a long time have the capability to be upgraded and then downgraded as they are sold, for example, into a market where active safety features would no longer be relevant, or where the life cycle, the reliability of these capabilities could not be guaranteed. So therefore they sort of eliminate that feature, but you can still use the truck, the basic capabilities of a truck. And then, as I mentioned, supporting a service-based business model. With 3D printing, we can think of actually having much more efficient, localized, distributed repairs, all supporting a circular economy. And then one further important takeaway is that when we are flooding the earth with electronics and software, we really need to make sure that that is modular and part of a circular economy itself, so that it can be reused, recycled. For example, now there's a lot of gold flashed as part of embedded systems in the connectors, I presume. So this is another very important aspect. And why am I raising this here? Well, because it's really an open research topic where we need to get people that are experts in economy, sustainability, and cyber-physical systems to work together. And you need to look holistically at this. And you have the value chains and the life cycle making this complicated, but there are a lot of companies also pushing this now. So it's a very relevant and an area where you can monetize. This is actually a way to create CPS and to turn sustainability into both an environmental and economically viable area. Okay, so continuing on this thread a little bit, so we are saying that with CPS we create all these new capabilities, and I wanted to show you an example here almost 20 years ago, 20 years old. 20 years ago, one hot topic was that of steer-by-wire. Think about a modern car, any car. It has a mechanical device, a steering column that conveys energy, forces, and information from the steering wheel to the wheels. A classical device. If you think CPS, if you think mechatronics, well, why do we need a steering wheel? We want to transfer force and energy, but we can do that in other ways. There are other designs. We can put an actuator and have energy here. We have a motor here that can steer the wheel, and we can use the communication network. Simsalabim. And what does this mean? Well, it means that we remove mechanical parts. We can create entirely new designs. This was demonstrated by General Motors and SKF some 20 years ago. So this means entirely new designs, exemplified by their concept vehicle. No mechanical linkages here, as you can see. They also had fuel cells in these cars. So potentially very environmentally friendly, entirely new designs, new possibilities for control, and so on. So wonderful concepts. Why did they not happen? Well, we had the example already with the Waymo automated cars, and we simply see that technology maturation may take time. If you think about hydrogen, fuel cells, well, the infrastructure is simply not there. We need to evolve the infrastructure. What about the steering rod, the mechanical components here that we removed in the concept car? Well, they're actually still mandated by law. It takes time for legislation to evolve. So here we have an example where we see that taking this shift to leverage the capabilities generally may take time. And as we saw for the automated vehicles, there are different hurdles on the way, if you recall that. So wrapping up on the CPS generalization here, CPS, well, one way to view them are as this integration, and that can be small systems, it can be large systems. This is not new, and what's important here is to look at the different types of CPS. But what is new are these entirely new capabilities, the increasing levels of integration. We saw that in the cyber domain, over edge up to the cloud, collaborating systems, deployment in all kinds of domains, integration over the life cycle, putting robots on the streets, open society scale, and the evolution of business models. So this is what is new with cyber physical systems. And we will, in the last part of this session, we will look at the implications of this in terms of a technical revolution, a socio-technical paradigm shift. But before we go there, I would like to take a little break with you and do the Q&A. And I see here 2 questions. If you have more questions, please just put them forward. So, Balaji, thank you for your question. The question is, I guess you can see them, but still I'll read them to try to understand. Not every research group will have a budget to build autonomous systems, autonomous cars. Hard to identify research questions without the platform. Okay, there's a lot of talk about safety and security, but without the complete system, it's hard to evolve. Okay, thank you, Mallory. I think this is really an excellent question. And it's very much related to the follow-up also, the complexity. So these systems are extremely complex. And to explore them, we really need to experiment. And how can we do that when we need, we need models of all kinds of things. I guess there are a couple of answers. One answer is that there are open source efforts here that may help you. I mentioned our ADI effort. I will come back to that in the next session. So ADI effort, we are leveraging existing open source and adding our own, making it possible for you to simulate an entire vehicle and an environment. And you have the functionalities already there. For example, perception, fusion, planning. You don't have to start from scratch. There are simulation tools evolving. There are lots of open source simulation tools. There are also some open test environments evolving where researchers can make use of embedded of cars or test drives. So I fully agree, and we need to make use of these. And I think this is slowly increasing, and it is a very important direction. So Alvaro, you had a question. Does this Netrunner example counts as well the testing? If I understand your question, it's really about. I talked about the number of lines of code, and does this expand also when it talks about the complexity of the testing? And basically, yes. So the more complex system, the more lines of code, the more states in your system, the more components, the more structural issues. So the larger state space, the larger amount of test cases. So I would say typically yes. And this is very much an open issue. When we go to these open systems, how do you deal with this increasing scale of testing, and how do you combine physical testing with, let's say, hardware-in-the-loop testing, simulation-based testing, formal methods, and so on. So, thank you very much for these questions. Please feel free to follow up on them. And I will then proceed to the last part here, CPS as a socio-technical shift. And I think we are doing relatively well on time. So, as I think pretty much clear in my presentation so far, we are talking about an evolution of systems with the new opportunities and capabilities which have a lot of implications. And when we talk about the technical revolution or a socio-technical shift, typically we see these things, at least these things, that we can learn from previous technical revolutions. A lot of new capabilities. We are seeing new companies emerging, old companies being removed from the market. They can't compete anymore. We are seeing acquisitions, coalitions, new collaborations, business models evolving, and new risks and challenges. And this essentially is what I would like to elaborate on. And firstly, I would like to show you the classical S curves. If you have studied technical revolutions before, you are very well familiar with them. But very briefly to introduce them, essentially the idea here is that you have this sort of, they are called S curves. And for example, let's take the example of the steam engine. The steam engine at once upon a time was an invention, a novel thing. It had much lower performance for being built into a system that could transport people and humans. The dominating transportation technology at the time of the 17th century and the beginning of the 18th century was still that of horses and carriages. And these horses and carriages had a much higher performance. But then as steam engines evolved, they were promising, but they were still clumsy, they were exploding, they were costly, but as they evolved, they got better and better performance, and eventually their performance just superseded and were much better than that of horses and carriages. And in that shift, people were desperately in that market trying to improve the performance of horses and carriages. They were trying to give horses better food, to reduce the distances they were running, to train their drivers, the horsemen, horse people, and so on. And they could squeeze out the last performance, but they could not outcompete the new performance. And this is really the idea here. And we see these throughout times in different S curves, how steam power, combustion engines, electrical engines are outperforming ordinary phones, smartphones, taxis, transportation services, and so on. And what does this mean? It means disruption and change. One indicator of this is the United States of America's Fortune 500 list, which has a list of companies, the top 500 companies economically measured, to my understanding. And there you can see that this list of companies is changing more and more frequently. More companies are disappearing, more companies are emerging. And right, I think there's some replication here, but in any case, we can see that digitalization is probably one of the factors here. Once you have a digital platform in place, you can launch things even faster. I will follow up on this shortly. And then I wanted to show you this classical picture of Kodak here. And there's a similar story of Polaroid. So this man was an inventor, probably might still be an inventor, but he worked as an inventor at Kodak. And at Kodak at the time, he developed the first digital camera prototype ever. At Kodak, which was at the time the totally dominating, world-leading company in producing cameras. They were leading the world market. They were selling, I think, in the order of millions of cameras per year. People were taking several photos a month. You know, they were dominating the world. And it was very hard for them to conceive a new world with using cell phones, where people were now buying billions of cell phones and taking hundreds of photos or more every day. It was completely out of their comfort zone. And this really shows the difficulty. We had the other example of Nokia having the total domination in mobile phones, and then the invention of the smartphone came. Thinking out of your comfort zone, being stuck into your legacy production, it's very hard to innovate inside your frame. So here's another example of a mechanical computing machine. That Kodak is, by the way, no more on the market as a company. Another a facet of this is if we look at so-called internet companies. This is actually very interesting, and it's evolving over the years. And you can see that this market of so-called internet companies is evolving. It's totally dominated by the US and China. These companies have in common that they are, many of them, very new. They have not been up and running for so many years. They have enormous revenues. And moreover, while they are called internet companies, that's only partly true. While they have a very strong internet basis, they are actually doing, to a large extent, cyber-physical systems. Amazon have factories with automated guided vehicles. They are planning to use drones. Google, well, they are also doing robotics and automated vehicles. And for example, we have Uber, transport services, and we have, many of them are in the internet, but also in the CPS market. And these companies now have an enormous power also, not only because of their revenues, but because they are getting hold of the data and knowledge about what is going on. I wanted to give you this illustration of how fast changes can happen in the digital age. This is an amazing picture from Stockholm Central Station. It's from 2008. If you look closely, you might see actually that people are using paper. They are reading newsletters or books. I think if you look very closely, you can see one or two cell phones, but you don't see a smartphone, because smartphones really had their breakthrough in 2009 here. So overnight, we had this enormous change, paving the way to entirely, not only technologies, but also entirely new behaviors. So we have disruption not only in technology and services, but also affecting behaviors of people, disruptive behaviors. And there are different perspectives and aspects of this. One view of this is given here by Industry 4.0. As we mentioned, the German view of cyber-physical systems, and they propose a view to look at industrial revolutions into revolutions that are more on the technological side. So the first industrial revolution was a lot to do with introducing steam engines and using water power that we mentioned as an example. So a lot of technological inventions. Then they mentioned, for example, the mass production. The technologies were basically there, but you were reorganizing. It was more of an organizational industrial revolution. Then we have the IT era, technological thing, and then they are emphasizing that what is happening today, of course we have lots of technological revolutions, innovations, but it's largely also an organizational revolution. So this is one view where we have lots of new innovations, they are brought together, and we have new business models, new ways of organizing technology. And and what I mentioned before, so when we introduce these new technologies, they're also coming along with new benefits, new performance, improved performance. That's why we introduced them, because we can sort of make money and we can facilitate life. But they also bring along new concerns and risks. And just to give you a few examples here, we talked about the automotive sector, and one illustrative example is that of active safety. And I'm sure you're aware of many of these things. So braking systems, automatic emergency braking mandated on many modern cars today. They will brake even if the driver doesn't notice something in front of your car. Airbags, electronic stability programs, saving lives if the car is losing traction. The car will try to stabilize itself. So we are introducing these new systems to save lives, and their statistics shows that this actually does help. We introduced these cell phones and smartphones to help to bring new services, and of course they help us with a lot of stuff. But as you can see indicated here, we are also starting to look downwards. It's changing our behaviors, sometimes not always for the good. We might become more vulnerable. That's one side effect. But these systems are also designed to really grab our attention. This, for example, this scrolling feature, the never-ending scrolling, uses a feature in our brains that looks for an ending. And if there is no ending, it's very hard for us to break out of this infinite scrolling. So it tries to use us as customers, get hold of our data, and keep us stuck. And that has side effects. And one side effect is that it actually reduces our intelligence. We become less smarter. Even with a cell phone from someone else relying on nearby will reduce our capability. And then there are these even more sort of scary things happening behind the scenes, that it's not only that data is taken from us, but these incentives are used to control our behaviors. For example, Pokemon Go is an example of that, which was, to my understanding, used to actually, as a business model, hidden to us, controlling our behaviors with emerging Pokemons emerging at some places to control our motion to go to certain places without us being aware of that. And then as we introduce these new technologies, of course, new technologies may fail, like the exploding steam engines that I mentioned. We have more cyber systems, more new vulnerabilities because of that, and especially because they are connected. So these things can be penetrated, people can steal things, or they can be hacked and controlled in ways that we don't want. And then even with the older kind of systems, this shows an example of a Toyota car, an older Toyota car, probably 15 years old or something. And at some point, these cars were suffering from unintended acceleration. They were accelerating and they were actually killing people. And when they started to accelerate, it was very hard for people to control that because it was a very stressing situation. And Toyota was found guilty in court for having design flaws in their mechatronic and embedded systems, posing new risks that people were not expecting, causing the deaths of people. So what is happening here? Well, to summarize, we are part of an industrial revolution. Herbert Simon summarized this very nicely in this anecdote, the steam engine and the computer, comparing these things. And as you have seen, and as we will continue to look at, technological revolution, there's more than one technology. It's not just, let's say, electrification. We also have new sensors. We have new computations and so on. The same goes for the steam engine. We needed new actuators. We needed new mechanisms. We needed new materials. And technological revolutions are slow. So the analysis is that the old revolutions took quite some time. And we are shaping technological revolutions, and the societal impact is not only visible until some time. And what is important here is to understand that we, as humans, we have this hyping feature. So we tend to overestimate. We are hype in the short term. A very clear example here is the automated driving. Very much hyped. IoT, very much hyped. But in the end, we are also most likely underestimating the change that will come when these systems are mature enough. So just to emphasize, we talked about gold rush for automated driving. Multiple technologies are developing. This is happening in many areas. In IoT, people are now talking about the 1,000 platforms. A lot of companies want to get hold of the gold, the prospects of making money on IoT-based services. AI, we are seeing these enormous investments. So lots of gold rushes happening in parallel. And I really touched upon this before. And I think the answer is pretty clear that innovation is progressing faster with digitalization. But when we talk about CPS, it will still take time because we need the cyber part, we need the physical part. And we saw the example, for example, in the steer-by-wire in the automated driving. But once we have the platforms, cyber platform and the physical platform in place, innovation can come much faster. And here the question is really when we have reached a stable level of that maturity for example, for automated driving. So Tesla has been betting that their cars can be upgraded. And of course they can be upgraded. Whether that will be sufficient to deal with, the capabilities of the sensors, of the computation, of the physical parts, that remains to be seen. You need a stable cyber physical platform. And as I mentioned before, we are accumulating knowledge and we can combine them. So we are really seeing unprecedented opportunities for innovation. And there is an extremely strong market push. So with these words, I would like to wrap up. I have a couple of wrap-up slides, but maybe before we go to them, let's have a quick look and take a little break and see if there are some questions. And I only see one by Yaganov. Okay, so it's a long question. What is your viewpoint as a scientist in this field? Does the CPS model aid in uplifting human lives ethically as a business model or as an economical standard? I think that's a very interesting and difficult question. I think it really matches very well where I ended up here. We have on the one hand these very strong market drivers, and new technologies will emerge whether we like it or not, because there is this big opportunities and potential to make money in transportation, for example. Technological systems can be used for good or for bad. It's not for granted that they will be ethical or sustainable. And if we just continue along the old direction, we will have this linear economy. But I think on the positive side, and as I think I will say in the wrap up, there's a growing awareness that we cannot just proceed as intended. Modern technology, cell phones, people are more depressed than before, even though the average lifespan is increasing. We have a huge sustainability threats in all aspects of sustainability. We have threats when it comes to ethics. I think there are clear signs that there's a growing awareness. I think also the corona pandemic shows that there is a possibility for us to act if we really take responsibility. So I think CPS can aid, but we really have to make sure this happens. And one challenge we need to deal with that we will focus on in the next session is how we can manage the complexity. So to wrap up, we have talked about automated vehicles as representative for cyber-physical systems, data and service age of interconnected CPS. And we see that similar developments in many domains. We have very strong market drivers. And we have to remember that we tend to hype in the short term, underestimate in the long term. We have to think about the new risks. We have the social technical impact. When it comes to CPS itself, I recommend characterization. A little bit of complexity comes to the dual interpretation of the word cyber. We need to leverage CPS for sustainability, and CPS have this new an inherent complexity that we really need to manage. And that's the topic of the coming sessions. One way to view that is that we have this strong market push, the innovations, let's say, pushing. We have the pull in terms of money or sustainability. And then one way to view this could be, well, one way to view it is that we have like an area that could be seen as barriers or opportunities. To build these systems, we need to think about, along the question we just had, what should the right properties be of these systems? We have to think about the risks, side effects, and so on. And we need the new tools, new methodologies and platforms to build these systems. The companies need to be ready. They need the right competence, they need the right collaboration, and not the least management. And then society needs to embrace and deal with these new technologies and systems. And that means that we really need to debate, educate, change infrastructures. So we are entering into these new types of cyber-physical systems. And perhaps for us as engineers and researchers, we understand a lot of these things, but they are, to an external viewer and perhaps to people not being into the technology, they are really like magic. Think about the remote control of a car, a modern keyless car or a remote control car. You know, the car opens automatically if we get close to it. How do these systems work? How should they work? I think there's an insight here, and Arthur C. Clarke, the science fiction writer, phrased that very well, that these future systems are really indistinguishable at some point from magic. And that relates back to how can we trust these systems if we can't understand them? How can we assess the risks, and including on the unintended effects locally and globally? And with these words, I would really like to conclude. And I hope you have enjoyed this little expose of cyber-physical systems, going into depth into automated systems, automated driving. And the next session, starting 1 p.m. tomorrow, we will be going into how we can deal with the complexity of these systems. If there are any last minute questions, those would be welcome. There was a question on the chat. A very relevant questions about the 500,000 lines of code, about the distribution of that. That's a very good question, and I will take that back to Atlas Copco. I've been wondering about that myself. I would think that quite a large portion comes from shared libraries and just the platform software, for example. But I don't have the distribution here right now, but I will investigate. I probably might not have the answer tomorrow, but feel free to come back to me later for that. I don't see any further questions. And here in Sweden, the sun is shining, and I will go out in the sun for a while. Thank you very much for your attention, and I hope and look forward to seeing you tomorrow. Thank you.